Hey, HillSauce, Ishaan here. Does 0.9 repeating equal 1?
In math class, you may have been shown an algebraic proof to this seemingly impossible idea. If we set x to equal 0.9 repeating, we can say that 10x equals 9.99 repeating. Subtracting the equations from one another, we get that 9x equals 9, and consequently, x equals 1.
Still, for many students, this answer seems too good to be true. Isn't there going to be some value, however small, some infinitesimal difference that separates the two numbers? Mathematicians have grappled with this idea of infinitesimals for centuries.
The idea of infinitesimal values was first explored by the ancient Greeks, who developed some of the early intuitions that would later become the basic principles of calculus. In particular, Archimedes began to explore the formulas for areas and volumes of curved objects, touching upon the basic ideas of integration. He discovered that the area of a circle is equal to the area of a right triangle, with one leg equal to the radius of the circle and the other leg equal to the circumference of the circle, by taking an infinite number of triangles with infinitely small width that eventually cover the area of the circle. Fast forward 1800 years, Isaac Newton and Gottfried Leibniz brought the concept of infinitesimals back to life while independently intuiting the ideas for calculus by using a change in y less than any assignable quantity divided by a change in x less than any other assignable quantity, for finding a derivative and multiplying and summing these small changes to find an integral. Euler expanded upon their work with infinitesimals in his book Introduction to the Analysis of Infinite, where he assumed that all of the standard rules of arithmetic applied to infinitesimals as well, though without any rigorous proof of this concept. By the late 19th century, most mathematicians were not convinced by the idea of infinitesimals, and they largely abandoned them and began the program known as the arithmetization of analysis, spearheaded by Cantor, Cauchy, Weierstrass, and Dedekind, who focused much of their work on developing the real number line from the rational. In most of the reasoning used in their work, they utilized the idea of arbitrarily small values, such as delta epsilon proofs or infinite convergent sequences, though never infinitely small values. However, in 1960, Abraham Robinson formalized the use of infinitely large and infinitely small numbers by showing how they could be defined using model theory and first-order logic. He termed such numbers hyperreals, and showed that all of the basic rules of arithmetic and basic functions that exist for the real number line also apply to the hyperreal number line, using the transfer principle. For example, the identity and commutative properties still hold true, as is the principle that the sign of an integer multiple of pi is equal to 0.
So what are hyperreals? Hyperreals are all the numbers that you already know, as well as these two things called infinitesimals and infinites. Infinitesimals are infinitely small numbers, while infinites are infinitely large numbers. What's different about the hyperreal number system is that all the numbers are represented by sequences. So basically, this sequence, 2, 2, 2, 2, 2, repeating, is a hyperreal number on the hyperreal number line. And it is equivalent to 2 on the real number line. And this brings us to equivalence classes. So if two numbers in the hyperreal number line appear different, they might not actually be different. If there are a finite number of differences between two hyperreals, they're not actually different. So what that means is that this number, 1, 2, 3, 3, 3, and so on, is the same as this sequence, which is 3, 3, 3, 3 repeating. So what about 0.9999 repeating? If we remember what we said about equivalence classes on the hyperreal number line, all the numbers in each sequence need to be equal to each other in order to be equal, or at least they need to be, finitely different from each other. Therefore, 0.9, 0.99, 0.999, 0.9999, so on and so forth, is not the same as 0.99 repeating and then 0.99 repeating, so on and so forth. Those two are not the same from each other. And since every single number in the first sequence differs from the second sequence, we can say for sure that it's not the same. So we can see that there is no hyperreal number that lies between those two sequences. And so we have no choice but to say that it equals 1, even on the hyperreal number line. For most of our lives as students, we've thought about math in the realm of standard analysis. Standard analysis provides us with a toolset of definitions and ideas that help us navigate the world. Still, thinking about math in only one way limits our potential to think critically about certain problems and solutions. With non-standard analysis and the hyperreals, we were able to more formally wrap our heads around the idea that 0.9 repeating equals 1. Beyond this problem, mathematicians have used hyperreals and other number systems to solve a vast array of other challenging problems. Ultimately, math is all about opening your mind to thinking about different perspectives. As we continue to learn and grow, applying a similar mindset can open your eyes to a whole new world of possibilities.